Well, we'll begin. The reason I'm playing this particular music is that, first, Mozart's birthday is in a couple of days, so happy birthday, Wolfgang. And the other thing is that the science we're going to talk about today was principally done by, you've seen the word Coulomb's law, was a contemporary of Mozart. Coulomb did his work about the same years. Coulomb was born, Coulomb, whom you'll hear a lot about in the course of your life here, was born in he's 20 years older than Mozart, and Mozart died in 91. He only lived to be about 35. He wrote about 800 pieces of music in his 35 years, a prodigy. But Coulomb actually outlived him. Coulomb lived till 1806. So he may well have heard some of Mozart's music. I would hope so. Make his life better. In any case, that's the connection, such as it is. Now, we began on the physics side talking about electric charge. Electric charge is the quantity of electric stuff. We don't, as I say, we don't know exactly what this stuff is, but we know that it does things, very important things. As you know from your studies already, that atoms are made of electrically charged particles. Hydrogen atom is a plus nucleus with a negative electron going around it. So you've had that a lot. We are going to just take it as a fact that such stuff exists, and we're just going to study its properties and see what we can do with it. It's one of those non-contact forces. As you saw, I was able to move styrofoam balls. Once they got some charge, I got the charge. Somebody asked, where did the charge come from? Why is the rubbing important? Well, the basic idea is, at least as I understand it, is that different things have different attractions for electric charge. Just as you know that, for example, you have sodium chloride. Sodium likes to give up electron. Chlorine likes to take electrons. Different materials have just different affinities. It's actually understandable by quantum theory. We'll get to that way at the end. But for now, let's just say that different materials have different attractions for things. So if I bring, as I did, say, fur in contact with styrofoam, if I give it the opportunity, the one that likes electrons more the electrons are the ones that move, by the way. The electrons will move to the one that likes them more. Let's just put it that way for the time being. If you go very deeply in quantum theory, you can explain why styrofoam, say, likes electrons more and sucks the electrons out of the fur. But for now, we'll just say there is this preference, a difference between how much they cling to their electrons. And if you give them the opportunity, like by touching them and even rubbing them so that I spread it around, they will jump over. We'll just take that as the sufficient explanation for that. But once it's electrified, then you saw that, for example, I bring one electrified body with respect to the other. I don't have to touch them. There is this influence of one upon the other. The one on the arm moved because it's lighter. It didn't take much push to make the arm move. I didn't feel the thing resisting me because I'm much bigger and stronger than this thing. But so there is this force field around electrified things. And this is one of those instances. As I say, it's actually very general because everything, all atoms, have a force field around them. And when you touch two things together, it's hard to say when the electron clouds actually overlap. So you might say that things never really touch because you can't penetrate one cloud into another. So in a certain sense, everything is non-contact. But that looks a lot more like contact than two balls over here influencing each other. So we think of that as a non-contact thing, just like gravity is a non-contact force. I don't see anything, arms or rubber bands or something pulling me down to the floor. It's just a non-contact force. Okay, and how did this get over to here so quickly? Okay, let me then indeed talk about this particular experiment. We're going to do this thing again. We're going to do it in a little more detail because I want you to sort of follow the process a little more in detail. But it all comes down to the behavior of charges, which could be summarized as, let me make sure I get them all here. First of all, we say that the charge is conserved. Now, conservation in scientific terms, again, I'm here using in the scientific way. It's pretty close to this street meaning, but not exactly. Conservation means that a thing isn't created or destroyed. That's what we mean in physics by conservation. A conservation of energy is that energy is not created or destroyed. It can be transformed from one form to another, but presumably it's not gone. And you don't create energy out of nothing. You can move energy from one form to another. Charge is like that too. Charge is, we don't know how to create individual charges. Like nobody has yet created a single electron, just out of nothing, or a single plus charge. We just have never done it. So we make it into a rule. They call them the laws of physics. I don't know why it's a law. It's just what we observe. And if somebody does it, well, you win a Nobel Prize and you overthrow that law. That's fine. That's fine. But as far as we know, we do not create. So charge, which we'll call Q, is not created or destroyed. What that could mean, and it does happen, is you can get a plus charge and a minus charge, so together they're equal amounts. Overall, you have nothing, and they can combine to give you nothing, no charge. This happens in the real world. For example, you can have a positive electron and a negative electron, and they combine, and they will give you something with no charge, namely radiation, electromagnetic electric radiation. But you see, nothing was created or destroyed. It was just transformed. You have the minus electron and the plus electron. Or what we can actually do also is you can put in radiation, and out comes a minus and a plus, but always a minus and a plus, never just a minus. So that's why we say it's a law. As far as we know, it's true. So that's one property of charge. Another one is that it comes in a minimum unit. Which we call E, the electric charge, 1.6 times 10. Well, let me not put down the unit. It comes in, we'll figure out what that is. Now, another way of saying that, whenever a thing comes in units, we have the physics term that's a quantity, and we say it's quantized. So that, when things come in indivisible lumps, we say that they are quantized. So we say that the electric charge is quantized. We've never yet seen a fraction of an E, but we see multiples of E. You are made up of multiples of E's. I venture to say staggering number of E's inside of each of you. I was just quickly trying to do the number in my head because 1 coulomb is, the number is something like 6 times 10 to the 16 e's is the unit we use. Mr. Coulomb's name has come up. Yeah. They just named it after him because he had done such good work. So the coulomb is the quantity of charge, and it's, as I recall the number, 6 times 10 to the 18th? Let me... Well, the number I do remember is that the quantity of E is 1.6 times 10 to the minus 19th coulombs. This might be 18. Let me see. I have it written down someplace. We can check. Whatever it is, it is. And that's a measured number. It was first measured, and I think you're going to have a homework problem discussing this. Let me put a question mark here. It was measured by an American by the name of Millikan, working at Caltech, at about the year 1912 or thereabouts, 14, something about 100 years ago. Millikan measured the magnitude of the charge, the elementary charge. What he actually did was he managed to get charge, as we do, by some kind of frictional method, and he put them on an oil drop, and he tried to see how fast they would fall in electric fields. And working backwards, he always got that the charge on the drop was a multiple of some number, like it was 1 times this, or 5 electrons jumped on, or maybe 6, or maybe 3. He couldn't really control it very well, but whatever he did, he always got multiples of this number. So he said, that must be the number that is the charge of these most elementary particles. But what you don't get is a half of that, or a third. So what we believe that is a fact, that all the charges are the same. And interestingly, even if the charge is negative, as it was here, if you have a negative electron, it's the exact same as that of a positive electron. Why it's that value, again, it's a mystery. If you can solve it, you're great. But it is what it is. And it's measured to be this to high accuracy. And again, the other thing is that there are these, as we already demonstrated, there are these 2 types, which I think it was Benjamin Franklin, maybe, who called them plus and minus. There's nothing more positive about, like something that has a negative attitude. We're not talking about that. They're just names. As I said, you could call them Sally and Jane, or Tom and Sam, or 1 and 2. It doesn't matter. They're just different. And they're different in the sense that the 4th property is that, which I think we saw in my demo, that if I prepare things to be the same, let's say I rub this with fur and I rub this with fur, that they repel. And on the other hand, if I make them differently, if I rub this one with fur and I rub this one with plastic, this gave the other, whatever it is, whatever this was, this is the opposite, and these would attract. So, unlikes, this is the 4th property, unlikes attract, and likes repel. Again, this is nothing personal, but I don't know if you're attracted to unlike people or you're attracted to like people, but charges, they go, if you prepare them to be unlike, they tend to be attract each other, and if you make them of the same type, they repel. So that's the fourth property that we know about of charges. This is our observations. It doesn't surprise you, right? You all pretty much knew all that. Okay. I just reviewed for the people, the few that may not have seen it all in one place. Okay. Now, as I said at the beginning, that one of the things about physics, of course, is that we do things quantitatively. And so knowing these things, which people even in 1700 would have known some of this, because they had discovered static electricity. In fact, you may even know that the word electra comes from the Greek word for amber. You know, it's a kind of a secretion from trees. It's kind of a yellowish material. Well, when you rub that, it tends to pick up static electricity if you rub it with paper. So the Greek word for amber, electra, became electricity. So obviously, if the Greeks had a word for it, they knew about it, and so all of this would have been known already many hundreds of years ago. But then people started doing things quantitatively, and that's where Monsieur Coulomb came in. He did experiments where he would do something like what we did. Namely, he had a torsion balance where he would hang an object and put some charge on it and try to play games with other charges coming closer. And so he measured this distance effect. You appreciate that there was a distance effect, because if the balls were far away, nothing happened. Only when I brought them close, something happened. I might illustrate that here rather more dramatically. I think, because you saw that if I rub two things together, I charge them up. Now this machine here is what's called a Van de Graaff generator. Have you seen this? It's nice. I don't know if you can see, there's a belt here that's driven by a motor, and the belt goes around, and down below it rubs against something. So the belt picks up charge, and the belt goes up to the dome. Let me see if I can open this for you. I don't know if you can see this. There's a little the belt comes around here. There's a little screen over here. So the charge that's being transferred up with the belt, conveyor belt of charge, is picked off on this screen. The screen is attached to the dome, so that it's like a conveyor belt, and the charge is then accumulated on the dome. I'll explain that. There's a little subtlety here. We'll get to it next time. But that's the basic idea. So this is a way of accumulating. So I think of it as my friction experiment on steroids. I mean, see, this thing is really going to go. It's going to pick up a lot of charge and deliver it to the dome. So much more so than I could do with my fur and plastic. So let's do that. Let's turn it on. And you'll see the belt will start to run. So it's picking up charge. And it's picking up charge. And picking up charge. Okay, now the thing is, there is a influence being built up here. But it has a distance dependence. And if I bring this dome here closer, finally it gets where the field is strong enough so that the field is strong enough because they're closer to actually break the air down. It's strong enough to pull the atoms of air apart and draw once the atoms are broken, they are charged. And they can deliver electricity across. The electrons can now jump across. So they're brought up here, and now they can jump through the broken down air. But it is space dependent. I don't like to get shocked, so I'll turn it off that way. I should wait, if we're going to do something crazy, I should wait till the last lecture. So at least we get through the semester. Okay, so... Yeah, so there's a distance dependence. Now, Monsieur Coulomb wanted to measure it rather more precisely than we just did there, and he did this more or less with his torsion, what they call a torsion thing, where you hang balls on a string, and you bring the thing through, and you measure the distance, and you measure the turning of the ball as it is attracted or repelled, and he could get quantitative measure of the force as a function of distance. I'll even leave his name up because we are talking about him. So, as you know, he measured, first of all, that the force is proportional to inversely as the distance squared. So if you go twice as close, twice as close, the force will actually go up 4 times. Then another clever thing that he did was very nice. What he did something like this. He took a charged ball, which he charged up like I did, and he went to an uncharged ball, let's say it was a metal, and he would touch the two together. So if he had a certain amount of charge on here, when he touched them, he figured, which is a pretty smart thing, that, look, the charge wants to get away from each other, so you probably end up with Q over 2 on each of the balls when you separate them, right? So he was able to say, okay, I have Q over 2, and he could measure the force by Q over 2. He could measure with Q, then he could measure with Q over 2, and he could play that trick again and maybe get Q over 4, and so on, and he finally ended up that the force ended up being proportional to the amount of charge that were on the balls, both Q1 and Q2, because actually they act on each other. So that's very nice. And so you end up with these proportionalities that they go as the bigger the Q on each of them, the stronger the force, and the further you pull them apart, they go as 1 over the square of the distance. Okay, that's very nice, but you see, now you have a little problem because this is a unit of force, push and pull. This is a unit of charge, this is distance. So you've got to have something to straighten out the units and also to give you the magnitude. So you have to measure this a constant. To get an equation, an actual equation, there's some constant that has to be measured. Again, it's, I'm sorry, monsieur, but bye-bye. There's some, to actually convert from some unit of charge and distance to convert it to force, to the actual force that's in a different unit. So you have to measure that, and we do. Let me see if I have... okay. Again, we realize that charge is sort of a quantity of stuff, as I mentioned before. And, okay, let me talk about the quantitative measurement. Yeah. So here it is, the Coulomb law, and the constants that measured by people like Coulomb, rather crudely in his time, but very much more precisely with modern equipment, is that the K is this number 9 times, I should remember it, 10 to the 9th. Now you see the units have to be fixed up. You have to get newtons per Coulomb squared, so it cancels out that, and times, the R squared is going to be sort of meters squared in order to straighten out the units, and you end up with a force. The force will end up in units of newtons. Now that's a very unfamiliar unit, I'm sure, to you, because we don't use it in the common world much at all, actually. Even the Europeans in the metric system, they measure, if you go into a store, you don't buy a Newton's worth of beef, which you should because it's a weight. We buy a pound of beef, right? A pound. A pound is a force. In Europe, you buy a kilogram of meat. Kilogram is mass. Oh, this is something that everybody's got screwed up, I have to say. It's really sad. But these are different as I mentioned to you, that this is one of the places where the common language is very faulty, and even scientists have trouble. The point is that we have two things. We have mass and we have weight. Now, in the English system, we use pounds, right? And we think that's sort of a measure of the amount of stuff, like a pound of meat or something like that. But actually, it's a weight, and it's a force. This is a force. It's the force of gravity. The unit for mass in the English system is something you probably never heard of, and it's never used. It's called slugs. See, mass actually is a measure of inertia or gravitation, which it turns out is about the same. Now, in the metric system, at least we use one thing that in the metric system. We use kilograms in the metric system, right? Kilograms. Go to Europe, everything is sold in kilograms. They never used the unit that newtons. If you went to a grocer in Europe and asked him for a newton of meat, he would be very puzzled. He might give you a fig newton, something like that. But a newton of meat, no way. So it's a little unfortunate. Things have grown up where this unit is used and this unit is used. Now, what's the difference? Really very simple. Mass is really the amount of stuff. So you sort of you count up the number of protons and number of neutrons. And no matter where you go in space or anything, you will always have the same number of protons and neutrons. That's the mass. On the other hand, weight is the attraction of that to some body, weight, to the Earth. So my favorite joke is if you have a weight problem, you can fix it very easily. You just go very, very far from the Earth and all the other stars in empty space and where there's no gravity, and you'll lose weight. Unfortunately, you will carry your fat cells with you, and your mass will stay the same. So that's the difference. So I have your instant weight loss problem solved. So, but we in science will be using this unit because this is a force. It's a force. Pounds are a force, and newtons are a force. What's the relation of the two? I think I wrote it down here. I think a newton is about a quarter of a pound. Did I write that right? It's about a quarter of a pound. So if you weigh 150 pounds, you would weigh about 700 newtons. And in kilograms, you would be 150 pounds is what roughly a half is about 75 kilos. Do people who ever weigh themselves in kilos? Anybody ever weigh themselves in kilos? No? Okay, yeah. Well, you would weigh about, you don't weigh in kilos. I mean, I'm getting mixed up with the street language and other. But if you will put on a scale in Europe, or there are scales here in America too, I have this scale where you can flip it and you can get your weight in kilograms. It's not really your weight, it's your mass. I hope you're as confused as everybody else at this point. But the kilos is used as weight. So your weight, 150-pound person, would be roughly, the connection is 2.2 pounds have a mass of a kilo, something like that, right? So if you weighed 150 pounds, you'd weigh about 75 kilos. But your real weight is something like 4 times a 150-pound person would weigh roughly 4 times as much, maybe 600 or so newtons. That's the honest way to do it, but we don't really do it in real life that way. But in this class, you better get answers in newtons if you're looking for the force. Okay, so that's really it. That's the quantitative statement of this attraction between the two. Now, what the physicists do, well, let's do a little quick question here. Suppose we put this little question. So you have 2 charged particles attract each other with a force F. Let me write it. Do I have it up there? Yeah. So what does it say? Could somebody read it to me? You have 2 charged particles, and they attract each other with a force F. Notice that the force of one on the magnitude is the same. It's just that they have opposite directions. So what's the condition? What do we change here? Sorry. Could you tell me? Read it. We change what? The charge by 2? Oh, Q. Okay. Okay, so Q goes to 2Q on both sides? Okay, 2Q. All right. And distance is doubled. Okay. And the question is, what happened to the force? Okay, why don't you think a second, maybe talk to your neighbor. Let's hear what you come up with. Meet your neighbor. Talk to your friends. Will the force be which one? Okay. Let's see. So what are our choices here? How many came up with F over 8? It goes down by 8. Anybody? No? Force by 2? Half as much? The distance is twice as far, but okay, no. Nobody was fooled by that. How about F? Hey, good. That looks good. At least it's a majority opinion. Science is not democratic, of course. There is a truth. But that's, okay, how about twice? Because the charges are twice? Anybody think that? You're intimidated. Okay, it's okay. We're not taking pictures. 8 times? No. So everybody thinks F. It's right. Because if you look at it, we had Q went to 2Q, and the other one went to 2Q, and R went to 2R, but squared. So if you want to do the math, you got 2 times 2 is 4, Q squared, over 4, R squared, voila, which was the original force. So you're right. Good. It's that easy. But good point. Now the other thing about this force is that it has a direction, and we have the concept of a unit vector, which multiplies this equation to give the direction. And the direction, there's different notations. Books have various things. I sometimes use this with a hat on it. And what it is the direction from the charge 1 to the charge 2, but it's divided by its own length, so that if you multiply this, it doesn't change the size. It only gives you the direction, and the direction turns out to be important because that's the way the force acts. So I don't know that I want to do this. This is an example you can do at home, which is kind of interesting. Well, you work it out. Here's the torture I dreamed up. You take somebody who sits in the back row, and you say, I want you to sit in the back row. I want you to sit up close. And if you don't, I'm going to put you in a machine where we're going to put a plus charge on your head and a plus charge on your feet, and they're going to repel each other, and terrible. Now, so he says, but I have my fraternity brothers are going to come, and they're going to stand here and push down so that they're going to counterbalance the Coulomb repulsion. So the question I asked him, if I put a Coulomb here and a Coulomb there, how many fraternity brothers would you have to put? It's just like how many angels on the head of a pin? How many fraternity brothers do you have to put on your head to keep you from being stretched? Sounds terrible, but wakes you up. So now I work it out. Well, actually, I work it out here, and you can check it at home. If your average weight is 150 pounds and is 4.4 newtons in a pound, that's 650 newtons per person. Now, if you figure out what the Coulomb repulsion of a Coulomb here and a Coulomb there, let's say 6 feet, say 2 meters apart, what that Coulomb repulsion is, you figure out a force of 2 times 10 to the 9th newtons. And if you have 650 newtons in a person, you would need 3 million fraternity brothers standing here to counteract Coulomb. So the Coulomb repulsion of a lot of charges, Coulomb is a lot. It's like 10 to the, I couldn't figure it out, 18 or so charges. That's a lot of charge, and it produces a tremendous force. It's the same as the weight of 3 million people. That's the force of Coulomb. So we don't really, I probably generated microcoulombs in this experiment here. So that's a lot of charge. If it's free, if it's exposed, how you would get 10 to the 18th plus charges in a space like that, it's a hard job too. Okay. Okay, here's some notation in my notes. I have to make certain notations. But then we have the question of, okay, this is one charge. How do I deal with many charges? And it turns out that's fortunately very easy. You just add up the effects of each, but because there's a difference in direction possibly, you have to add them as vectors, which can be a little tricky. Now, I do have... and the other thing is that what we do, the other main idea, is we represent the influence. What we say is that even if there were not 2 charges to field force, it's sort of reasonable to say, even if you had 1 charge, something's doing in the space, even before you put something in. It's a guess, because you don't know because you haven't looked. But we imagine that this influence is out there, and all we've done is if we introduce another charge, this charge feels that influence, and we call that influence the electric field. It's the influence of this charge. It might almost be called the emanation, if you want to have another E, the emanation coming from a charge. So what it really is if the force is equal to the Coulomb thing, K, Q1, Q2 over R squared, what we do is imagine this Q2 is very small. And so we simply divide the force by Q2 and say, if Q2 weren't there, you would have Q1 producing this emanation, this thing, and that we call the electric field. So it's sort of out there even before we test it. It's a little bit of an abstraction, but a very powerful one. And it turns out, well, it turns out to be extremely useful. So that's the concept here. The electric field of a point charge is you simply divide by a test charge, a very small one. Because what you don't want is for when you put this charge in, that suppose there are a bunch of them, you might distort the distribution here when you bring in your test charge. For example, it might turn like that. No, you don't want to do that, see, because then the distance has changed, so the emanation of this pair would be different if it were this way compared to that way. So you want to make the test charge so small that you're not disturbing what's causing this source field. This is more or less the source, and it produces this field, and this is just a test probe. So, so we have, that's the idea of the electric field. Apparently people have trouble with that. I'm not exactly sure why. But, so you have a source field which is producing the field, and if you don't change it and you just put another charge in there, that would be the way to measure the field. Now, we have to have ways of representing it. I think this is a nice map, comes from the weather people, and I don't know if you can see that they've indicated, here's Berkeley. Oh, my God. And the weather temperature is indicated here by these little thingies they put on, little things like this. Now, on the one hand, they put the temperature in here, and this represents the wind direction. This is a weather map, and the number of barbs here tells you the velocity of the wind. So this is kind of a representation of a vector-like quantity, the wind direction, because you have two things. You have the wind direction and the speed, whereas temperature has no direction. It's maybe a little unfortunate in this map. They put the two close together, but temperature has no direction because you could have a temperature here and you could have another different temperature here. You could have a gradient of temperature, but the temperature itself doesn't have a direction. But the wind certainly does. So that's one representation. And we in physics use something like that. But you can see it's a common problem. Here's another. I was interested in weather things. Another way of visualizing wind vectors. You see, the vectors have different lengths and they have different directions to try to indicate the flow or the direction of the wind. So everybody who worries about things with direction and magnitude needs some way of representing it. We have in physics several ways, in fact. One of them is simply to, I don't know why I can't move this thing. In any case, as you can see up there, I have a source charge, the big negative, a ball with negatives on it. Now that is my source in this particular example. And I put a little positive test probe. Now I can understand how to say a pusher is the source is pushing things on it. And so the opposite of that might be push E, the thing that's being pushed. And the little test charge is there, and it's sensing the field. Now, one way of representing that is just to show these emanations coming out of the minus charge, and you can get a feeling for the strength by the density of lines. In other words, as the lines converge, they get more dense. And so you could say the field is stronger there, which we know. And as it goes out, it gets weaker because they get less tightly packed. So that's one way of representing it. Another way is simply to make arrows of different lengths so that, as you see here, an arrow that starts close to that plus charge is longer, and an arrow that starts further from the plus charge is shorter. So it's a way of saying how strong the field is there, how big the push would be if I went there. And also the arrowhead shows you the direction. The plus charge is, because our test charge is, by convention, is plus, so that plus charge would push it away. Whereas the arrows here point toward the negative charge. That's the way a plus charge would go. Now, okay, so then we come to the idea, okay, so suppose I have two charges. What do I do? Well, here is a very important example. I'm sorry. Dipole. Now, why is a dipole important? Well, I think we started to talk about that last time. Namely, if you simply put an uncharged object, like I did here, I had the styrofoam ball, and I brought a charged, say, a ball near it, it moved. But this thing is not charged, so, Q is 0 here. Started out 0, and so I have some Q here from the fur. But according to that formula, there's no force. So why did it move? Well, there is a good reason, and that is that inside of these things, there are atoms and molecules, and they're made of plus and minus charges. Now, they sense this field. Let's say the field like this, coming out of here, like I showed. Okay, so that says the plus charges should move that way, and the minus charges should move this way. So what actually happens to this Q equals 0 ball is that the minus charges are going to come this way. Even if they can't move far, they will move a little bit, and you'll stretch the molecules. You'll pull the negative charges this way and push the positives this way. This gives you what's called a dipole. Di meaning two. It's sort of similar to bi. I'm sure you had in chemistry dimers, trimers, right? Di is 2. Bi is binary, bits, and all those things is 2. Okay, so it's a dipole, 2 poles. And the reason this thing moved and was attracted, no less, is easy to understand because what happens is the charge distribution is stretched, the negatives get closer to the positive, and the force, because it's falling off, is 1 over r squared. The negative to the positive is stronger force than the positive is repelling the positive. So what we have here is, I think I've used the word, induced dipole. And that induced dipole is attracted to the source that made it. Now, I wanted to show you one more thing because I would like you to maybe play with this over the weekend if you have time. Let me try to find it. It's a animation of it's on the University of Colorado has done some very nice educational things. It's called PhET. It's Physics Educational Technology, U of Colorado. And this one it's actually, I think it's in your Mastering Physics. I think it's called Charges and Fields. And it's really cute to play with, and you get a feeling for the subject. What I'm going to do is I put on a grid, and what they allow you to do is put some charges out here. Here's a plus charge. Let me put it, over here. And then I can show the E field. Can you see this? I'm going to show the E field line. Boop. Okay. Now, so it shows you the lines, first of all, they're going out. Their scheme for showing you the strength is by the darkness of the color. You see how these guys out here are weak, and this is strong? That's their method of showing strength. Okay. Now, I can make a dipole. Take a negative charge and put it, say, here. Whoop. And what you can see is that the lines come out of the plus charge and they go into the minus charge. So this is the shape of a dipole field. And that's what's going on here. When I polarize this material, I induce something like this. Now, when you read your book, I want you to make a very important distinction. There, in the book, he talks about dipoles being rotated in a field. You have to make a distinction. Ooh, wire there. You have to make a distinction between an induced dipole, and this is a failing in the book, mind you. I must write to him about this. You have induced dipoles where you take an uncharged thing, you put it in an electric field due to something, or you just have a field here, and it'll move the minus charges this way and the plus charges that way, and you induce a dipole. Right, because the plus charges move, no, plus charges move that way, and minus is that way. The electric field moves the plus charges away from them. You can see that because if you put a plus here and a minus here, clearly the plus is going to want to run away from the plus. You can always check yourself. Now he conflates that with a permanent dipole. There are certain materials or molecules that have this feature built in. And one of the most important of these is water. It's a very important property of water that it is its own dipole, even in the absence of electric field. Very important. I will be drawing this many times. It's one of my things where it's my Mickey Mouse thing. Water is oxygen with hydrogen. And they are displaced. There's like a 100-degree angle between. You familiar with this from chemistry? Because of the chemical bonding. So this has a dipole because the hydrogens lose electrons, and the oxygen being attractive to electrons. You see, you have a dipole. The dipole is from minus to plus. So this is a permanent dipole. And it's very important. It's very important for the properties of water that it's a polar material. So when he talks about, I put an electric field and my dipole rotates, he's talking about this kind of dipole. If you were talking about this kind of dipole, what would happen is you put on the field and it creates the dipole. It wasn't there before. And when you rotate the field, the dipole is being created and will follow the field practically instantly. All the electrons just follow, because the electrons can move fast. This other guy, the whole molecule has to turn. So it's very different. And so when you hear about induced versus dipoles, you must keep that in mind. We'll talk about that later, but it's an important idea for you to grasp. Thank you. Have a good weekend. Oh, by the way, I'll post homework tonight, and it'll be due next week on Friday. And by the way, you can play with this animation.